publishing my talk a little bit because there were some typos, etc. there, but when Vlog said that immediately you have to leave this talk, so I have given that one, so it must have some typos and all. Okay. And also I thought about discussing a few, whatever I understood of Professor Sinha's work on dark matter, I mean the machos, the strange quark nuggets as dark matter. That was under preparation, but that I didn't get the time because of this sudden request to give the talk in somebody else's place. However, let me begin with what I planned earlier for my tomorrow's talk. That is, to say 2-3 sentences of that strange quark nugget machos as dark matter. So the idea started from Wheaton's famous 1984 paper that during the QCD phase transition, if the phase transition occurs from via bubble nucleation, then there can be nuggets can be produced in that medium. That means in that medium where the quarks are transforming into hadrons, there these hadrons, during the bubble nucleation, the quarks can be trapped inside, and those quarks can produce quark nuggets with the up, down, and strange quarks. And Professor Sinha and his collaborators like Professor Raha and Jane and others showed that what should be the baryon number of those quark nuggets to be stable. That is around 10 to the 42 or something. But then later, they have extended their work to propose that the machos, or massive astrophysical compact halo objects, which can be a potential candidate for dark matter, could be produced by the strange quark nuggets. That means during this QCD phase transition, the nuggets of strange quarks are produced with some baryon number that they calculated out. What should be the baryon number to qualify themselves to be those strange quark nuggets to be the machos? And they have shown in their famous MN-Ras paper that indeed what should be the baryon number or the number of quark nuggets in some volume of space, so that can be called a macho, and that can account for all the dark matters in the universe. So, having said this, let me come to my talk. So this is also related to dark matter, but there is a slight introduction of dark energy also, not in very detail, but here actually what happened, there is something called 21 centimeter H1 line. 1 means neutral hydrogen at its ground state. So this 21 centimeter line can be utilized in many respects to probe the early universe when other signals may not be that eloquent. And so first I start with what is the 21 centimeter signal. I mean, anybody in this audience knows that this is a hyperfine transition of the neutral hydrogen atom at its ground state. That means if the nucleus spin and the electron spin are in the same direction, that state 2, or 2 and para state actually, 2, when one spin is flipped, that means there can be 2 states, 1 and 0, triplet and singlet. The transition between this singlet and triplet state is the 21 centimeter transition. And we know where the early universe, it is full of hydrogen, 75% mostly hydrogen and 25% helium. So these neutral hydrogens can give rise to 21 centimeter signal. And obviously when it reaches us now, it is redshifted highly. So we measure some other wavelength, but but then calculated out whether this 21 centimeter signal came from what age of the evolution of the universe, and from there try to extract physics, even the physics of dark matter also. So let us skip this because this is not in that order what I have written in the plan and all, because I wanted to shift or reshuffle something which I didn't get. So what I was saying here is this. This is the triplet state. This is the nucleus spin, same direction. This is the electron rounding it. And after the spin flip, this is the singlet state. And this hyperfine transition of these two states is what gives rise to 21 centimeter photons. And the energy difference between the two, I'm sorry, what is that? So the delta E of these two states can be calculated out to be this. And the population of the triplet state and the singlet state, don't consider in para, in antipara, etc. This is just the this triplet state N1 by N0. Let us say N1 by N0 should be equal to, this is the degeneracy factor for 1, this is 3, and this is 1, 3 by 1 exponential T star by Ts, where T star is h nu 21 centimeter this energy by K Boltzmann constant. So N1 by N0, the population of the triplet and singlet state is given by a quantity which you see, which is called the spin temperature. And this spin temperature is something very important in the evolution of the 21 centimeter line, or this 21 centimeter transition from the very early stage of the universe, just after the recombination and the photons was free to move. From that, via the dark ages to the ionization time, reionization time, when the first star was born, that is the cosmic dawn, and later. So in some cases we get the 21 centimeter absorption signal, and in some cases we get 21 centimeter emission signal, and that will happen roughly because this 21 centimeter line, we are looking at the background of the cosmic microwave background radiation, or CMB. Therefore, if TS is greater than TCMB, then we get emission line. TS is less than TCMB. CMB means cosmic microwave background temperature at that epoch. Then we will get absorption line. Okay. So this is just cartoon that says that this is a full of H1 gas. H1 means neutral hydrogen gas, not ionized. And then there is TS, signifies the relative abundance of the triplet state and the singlet state. And this is the optical depth of this gas, and we are looking at the background of TCMB. And in this situation, this delta TB is wrong. Actually, this should be T21, the 21 centimeter brightness temperature. I'm sorry, I didn't get time to replace it with T21. T21 is given by the difference of TS minus TCMB, and of course the redshift. This is the redshift. And this is the optical depth of the gas. But now, this, as I just said, there are 2-3 temperatures involved here. One is, this spin temperature is, of course, is defined in that way, but there are CMB, cosmic microwave background temperature, there is gas temperature, and their correlation, combination, etc. That actually determines this T21. Okay, so this is just at what redshift, what should be the wavelength, etc. So 0 redshift 21 centimeter at 19, redshift is 19, and that time actually reionization, onset of reionization, first star came into being. Then it will be 4.2 meter, it has become about 71 or 78, I think it should be 78 megahertz. The one that I said, N1 by N0 that I just defined, N1 by N0 is given as TS, and T star, which is H nu 21 by K, and G1 is 3 by 1. And here, okay. So this TK here is the gas temperature. Gas means that hydrogen gas, full of hydrogen gas, that temperature. Now it has correlation, different correlations. This TCMB, which is actually the free movement of photon after Z is equal to 1100, that means something like 300,000 Earth year after the Big Bang, when this recombination is complete and there is no spare electron left with which the photons can scatter. That means the photons are free streaming through the space, through the universe, and with the expansion of the universe. But that was not so. I mean, just after that phase, the Compton scattering is still there because there are still some electrons, and the density is more. The Compton scattering continued. So this Compton scattering of those photons, free streaming photons with the residual electrons, that can heat up the gas, and this excitation or de-excitation of the 21 centimeter line, whether 0 to 1, 1 to 0, etc., affects this TS, or TS is determined by that, because TS is that N1 by N0, which is the ratio of the triplet and singlet state in that hyperfine structure. And there can be collision of these gases. I mean, within the gas. I mean, the gas is hydrogen. I mean, in cosmology, everything is said to be baryons. I mean, whether hydrogen gas, whatever, everything put together is baryons. So there can be collisions that also give rise to temperatures. And this is something interesting. When the first star is born, that is in the cosmic dawn, after the dark ages, then what happens? Here the neutral hydrogen, I mean, the universe is full of 75% of the universe is full of neutral hydrogen. So at the ground state. But the ionization starts means I will get the Lyman alpha line also, because it is pumped up and coming down the electron. So Lyman alpha line, as we all know, this Balmer series, Lyman series, Paschen series, bracket series, etc. So Lyman alpha will come, which is the transition from the upper orbits to n is equal to 1 orbit. And this Lyman alpha plays an important role in tuning this TS, or the population of N1 and N0. So the Lyman alpha couples with the gas, with the gas TK, I mean the hydrogen gas of TK, and then it controls this spin temperature. One thing I think I forgot to, this is TS minus TMP. So this T21, the 21 centimeter brightness temperature, is to be expressed in terms of TS minus TMP. If so, TS is less than TCMP, then it is a negative, or TS is greater than, then this is a positive one. Okay. So this is just a cartoon. And what happens actually? This 1100 is the time when the photons were free streaming, but not quite, because the Compton scattering still is there. So up to Z is equal to of the order of 200, the residual free electron, as I just mentioned, allows Compton scattering to happen, and this Compton scattering actually stops at Z is equal to 200 when the Compton scattering time is actually more than the Hubble time, then only it stops. So, so that time, the TB is the baryon temperature, means the gas temperature. This follows the CMP temperature. And this high gas density leads to effective collisional coupling, so that the spin temperature also in equilibrium with the CMP temperature. And if Ts is equal to T gamma, there is no T21, I mean the T21 signal, because we have seen that T21 is Ts minus T gamma by something Z plus 1 into exponential this attenuation of tau. And then from 200 to 40, the gas cools adiabatically, because after this actual decoupling occurs of the photons from the matter, and then it cools like 1 plus z square, whereas the CMB also cools but goes as 1 plus z. So this gas temperature or the baryon temperature goes as 1 plus z square, and then Tb is less than T gamma, and collisional coupling also makes Ts less than T gamma. So T gamma is TCMB actually. So Ts minus TCMB, so we get a early absorption signal. But this is also not the signal from the cosmic dawn time when the first star is formed. When this Z star, some Z, actually this is the reionization Z, which is around that 2019, 29, etc. It is approaching that cosmic dawn. Expansion continues, decreasing the gas density. Collisional coupling becomes ineffective because the density gets reduced more and more. And the coupling is only radiative coupling. So T gamma then follows Ts. Ts follows T gamma, and there is again no signal, 21 centimeter signal. But then, within this Z alpha, alpha means this when the ionization took place and Lyman alpha line we are getting. So within that Z, this is what is written here. Once the first source is switched on at Z star, they emit Lyman alpha photons and X-rays. And then Lyman alpha, what it does, it makes the spin temperature to be the same as the gas temperature. Both are less than T gamma. That means, and then we get a 21 centimeter signal. Okay, so this is a various factor is involved in getting 21 centimeter signal. But this AGES experiment in Australia, which looks for 21 centimeter signal in the cosmic dawn era, they have measured that 21 centimeter signal from the cosmic dawn time. And what they get is an anomaly. They get a dip here. It has to be a dip here because Ts is less than T gamma, so Ts minus T gamma is negative, but not this code, not this dip actually. So what they got is a dip at minus 500 degree millikelvin, plus or minus plus 200 millikelvin, minus 200 millikelvin. That means from minus 300 to minus 1000, centered at 500, minus 500 degree millikelvin. This dip is around the Z, which is around 19 to 16, which is the cosmic dawn time, the reionization time when the first star is coming out. Ionization and emission, so star is coming. So, okay. So this is an anomaly. So what one expected that it should fall up to this 200, minus 200 and then go up, but instead it goes up to the minus 500. Okay. So there are then people try to explain in different ways, like the primordial black hole evaporation, dark matter annihilation, etc., etc. But here we took the dark matter baryon interaction, the scattering, as also the possible dark matter dark energy collision or dark matter dark energy interaction. How these two can affect, whether this, if we introduce these two, whether we can explain this. But then also what we can do, we can, taking this as the standard, we can say what could be the mass of the dark matter or weak dark matter for which this is satisfies if dark matter baryon interaction, baryon means all other particles actually, dark matter other particle interaction is taken into account along with dark matter dark energy interaction. Okay, so dark matter dark energy interaction actually produces heat or takes out heat from the system, and that makes the system cool. That is one possibility. And dark matter baryon interaction also can give the system heat or can take out heat, depending on whether the dark matter is heavier or lighter than the baryon, in general baryon gas outside. This is taken from other people's research that so the heat is important. So the heat produced or taken out due to for this kind of dark matter dark energy interaction are given by these two equations. So we are going to use this. But certainly if this term is there, the Hubble parameter will not go with Z following this, what we know from cosmology, this relation. Omega is that dark energy equation of state. So Hubble parameter will change. Okay. But what dark energy model will do? But model one, not dark energy model, for the model for this heat exchange due to dark matter dark energy collision. So these are some phenomenological models. Is given by this lambda, which is the dark matter dark energy interaction strength, and this is rho d means the dark energy density, rho k is dark matter density. So these kind of three models are proposed, and those are tested also by different observations. And if you take this model 1, these two from model 1 and model 2, model 3, I should have written that. So model 1, the equation of state for dark energy is minus 0.9, and this interaction strength 0.1, and H0, the Hubble parameter considered in the lambda CDM model for cosmology is this 68.1 in the Hubble parameter unit, megaparsec per second per second. Okay. So these are some phenomenological expressions for Q. Okay. Now first, plot this Hz by H0, how it varies for three models. We take lambda is equal to 0.1, it is just a demonstrative plot, although lambda is different for three models, but we have taken lambda is 0.1.